All right, so obviously things are going to be a little bit different because of the arrangements that we have needed to make in the current circumstances, but we're going to get right back into precalculus stuff. So we're going to be moving on from talking about exponential and logarithmic functions, and we're going to start talking about the subject of trigonometry. And broadly speaking, this involves the study of things involving triangles and circles. So the first thing we want to talk about are going to be angles. And how do you measure an angle? Well, one way that you're probably familiar with measuring an angle is to measure it using degrees. So the idea behind using degrees is that if I have some sort of a circle here, I can take an angle in this circle, and we're going to call this angle theta. This is a Greek lowercase theta symbol. It's one of the letters in the Greek alphabet. And the way that we measure how big this angle is we essentially look at how much of the circle is inside of this wedge. Well, if you measure something in degrees, we divide the circle into 360 pieces. So in other words, I'm going to take this circle and I'm going to kind of, around the edge of this thing, I would mark out 360 different points. And each one of these thin little wedges, and of course this is going to keep going, we're not just, marking it out here. We mark all the way around the circle, 360 points, and we space them out equally. And each one of those little angles that we put is going to be 1 degree. So this is one of the ways that you've probably seen to measure angles before. And so a full circle, well, a full circle, based upon the definition that we've given here, is going to be 360 degrees. That's just the way that we've defined the degree angle measure. And if a full circle is 360 degrees, then half a circle, so if I were to just take 1/2 of this thing, well, this would be 180 degrees. And to mark out that these are degrees, we use a little symbol that is like a tiny O shape or a zero shape, kind of. So half a circle would be 180 degrees. If we went around 1/4 of a circle, well, 1/4 of a circle is going to be 90 degrees. And a quarter circle angle is also called a right angle. These right angles are pretty important in mathematics. We're going to be returning to this repeatedly throughout this course. So a right angle, though, in degrees is just 90 degrees. And there's a few other angles that are important that we'll come back to and talk about their measurement in degrees. Now, degrees turn out not to necessarily be the best way of measuring angles all the time. Okay, so engineers like to use degrees. Degrees are pretty convenient for some uses, but they're not necessarily always the best way to measure angles, even though they're probably the most common that people learn when they're first learning about angles and things like this. There is a somewhat better way for some purposes. Again, all these ways have their advantages and disadvantages, but there is a slightly better way for a lot of cases in mathematics. And this second way of thinking about angles, or of measuring angles, it really relates back to the geometry of a circle. Because if we're thinking about angles, this kind of naturally relates to circles. You saw how, well, even with degrees, we're defining degrees by saying, okay, 1 degree is 1 out of 360 of one circle. So this other method of measuring angles comes from thinking about the following fact, which you probably remember from geometry, hopefully remember from geometry. So the circumference of a circle, and let's say that this circle that we're talking about has a radius of r. Well, hopefully you guys remember what this is. The circumference is 2 pi times the radius. So, one way that I could think about how much of an angle do I have is if I take some circle, and let me put some angle in here, and we'll say that this circle has a radius of r1. Well, I can think about how long is this piece of the arc, okay? And that would be one way of kind of thinking about how big is this circle. I could think of what is this length along the circumference of my circle. If I were to go all the way around the circle, I would go a distance of 2 pi times the radius. But we kind of want to think about the angle in a way that it doesn't depend upon choosing a radius for our circle. I don't want to measure angles in a way that depends upon specifying a circle with a specified radius and thinking about things that way. I want to actually specify a way of thinking about angles that is completely independent of what circle, what radius I happen to choose. Fortunately, there is an observation that we can make at this point, which is, if I think of this length here as, let's just call the length along the edge of this wedge L. Actually, let's call it L1, because I'm going to draw something new here in a moment. Now, let's suppose that I make a bigger circle, or it could be a smaller circle, but just a circle with a different radius here. That's a terrible looking circle. Let's see if we can make it a little bit more circular. Okay, so now, let's suppose that this new circle has a radius of R2, and that over here, the length along this arc on the bigger circle, I'm going to call that L2. Well, the thing that you might observe here is that because we've just increased the radius by a factor of R2 over R1, we also increase the length of this distance along the circumference by the same ratio. In other words, what we see is that L1 over R1 is equal to L2 over R2. So, the length that I cut out of the circumference with a given angle, in this case the angle I've called theta, that is going to depend upon what circle I choose. So that length changes based on my circle. What does not change based on my circle is this ratio. The ratio of this length here, whatever length I've cut out along the edge of the circle, to the radius of that circle, that is constant. So what we can say is that the arc length, and the arc length just refers to what I've called here L1 and L2. Sorry, I'm getting in the light over here. Hopefully you guys can see okay. The arc length refers to L1 and L2. The ratio of the arc length divided by the radius, this is actually a constant that only depends upon how big this angle is. And this number, the arc length divided by the radius, this is the measurement of theta in a kind of units which we call radians. So, radians provide a different measurement for angles than degrees. It's a similar idea, okay? It's very similar to degrees. When we're talking about degrees, we're breaking up the entire circle into 360 pieces and basically asking how many of those pieces does our angle cut out. in this case, instead of breaking it up into pieces like that, we actually just say, well, okay, let's just measure what is this arc length, what is the length along the circumference here, then we'll divide it by the radius of the circle, and that gives me my radians. Now, one of the reasons why this is so convenient mathematically is because of the following fact. As soon as I get this erased, I can write down this fact. So, if theta is in radians, then the arc length say L1 here has a very nice formula here. It is actually just given by L1 is equal to R1 times theta, as long as you measure theta in radians. And that's the important thing. You have to have theta in radians in order to have this nice relationship. But this relationship is so nice that it ends up making a lot of things in mathematics work out in a very neat way. We don't get a lot of extraneous factors or constants or anything coming into play, as long as we are willing to measure everything in radians when we're talking about our angles. Now, one of the things that we want to be able to do here is we want to be able to convert back and forth between measurements in degrees and measurements in radians. So let's just quickly think about how would that work. Well, the way that we're going to figure out how that works is we're going to start by asking ourselves, how can we talk about different kind of standard pieces of our circle in terms of radians? Now, if you remember, I said a few minutes ago when I was talking about angles in degrees, I said a full circle is 360 degrees. So let me put a picture of a circle up here. Hopefully you guys can see this okay. Here is my circle, and we said a full circle, well, that's going to be 360 degrees. That's just how the degree is defined. Now, how big is that same full circle going to be in radians? Well, we defined the radians to be the arc length divided by the radius. And if I do a full circle, for a full circle, the arc length is the circumference. So take a moment and think about what would that be in radians. If I take the arc length, which is the circumference, and I divide that by the radius, what am I going to get? You can pause this for a moment and think about it. I would encourage you to take a couple minutes and see if you can work this out. After that, well, if I call this radius r, then the radius, the circumference, I'm sorry, not the radius, the circumference, which is the arc length for a full circle, is going to be 2 pi times r. So that is my arc length in this case. It's literally just the circumference, which is 2 pi times the radius. And that means that in radians, I take that arc length, 2 pi r, and I divide it by the radius. So I'm going to get 2 pi times r divided by r. Well, what is that? The r's are going to cancel, and we get 2 pi. So a full circle is 360 degrees on the one hand, but on the other hand, it's 2 pi in radians. So one full circle is 2 pi. I should actually mark down that this is in radians, which we often abbreviate as RAD. So one circle is 2 pi radians. It's also 360 degrees. And this gives us a ratio for how do you convert back and forth between radians and degrees. So what we can say here from this is that 1 degree is equal to 2 pi divided by 360 radians. Well, think about that for a moment. I can actually simplify this expression just a bit because I can cancel out the 2 and the 360, and I can say 1 degree is equal to pi divided by 180 radians. Now, if I take this, I can then use that to convert it to give me radians in terms of degrees, so I can say that 1 radian is equal to 180 over pi degrees. So these are your conversion factors for going back and forth between radians and degrees. These are pretty important to remember, but they're not too bad to memorize. The way that you want to memorize them is think about where they come from. Think about the fact that a full circle is 2 pi radians, and it's also 360 degrees. If you remember that, then it's pretty easy. You can always just kind of remember this formula, and then you rewrite it in whatever form you happen to need, depending upon what the problem is that you're dealing with. A few other important angles that we can talk about in radians. A half circle, we said this is 180 degrees, but another way of thinking about half a circle is it's half of a full circle, which is 2 pi radians. That means that it is also pi radians. 1/4 circle, well, we said that this is 90 degrees. Sorry, that 9 was pretty terrible. 90 degrees is 1/4 circle, but it's also 1/4 of 2 pi radians. Well, 1/4 of 2 pi radians is going to come out to be pi over 2 in radians. So we have these different angle measurements that we have for the circle, these important pieces of a circle, the whole circle, half the circle, 1/4 of the circle, and we have them written down in both degrees and in radians at this point. We also know how to convert back and forth between radians and degrees. Now, if you're feeling like you want to take a minute, go back and review this for a bit and let it sort of sink in, feel free to do that. Otherwise, I'm going to go on and do a few examples of converting angles between degrees and radians. So, let's suppose that I want to convert let's say I want to convert 30 degrees to radians. Well, all I have to do, this is just a basic unit conversion problem. It's using angles, which are measured in degrees and radians, but it's no different than if I wanted to convert feet to inches, or if I wanted to convert, yards into feet, or anything like that. Maybe I want to convert pounds into kilograms. You do all these problems in the same way. And so what I'm going to do is I'm going to say that 30 degrees, and I want to get rid of the degrees, so I have to multiply by radians per degree. Well, this is going to be pi radians per 180 degrees. Now, you might notice that when I wrote this, instead of using the little degree symbol, I wrote out degree. That's just so that I can do this. I want to say, hey, I just canceled out my degrees. If I just had a little degree symbol, it'd be very difficult to do that in a way that would be easy to see. Okay, so what we end up with is 30 pi divided by 180. And, of course, 30 over 180, that's the same thing as 3 over 18, which comes out to be 1 over 6. So, we end up with pi over 6 radians. Oh, and I forgot my radian units up here. So, usually when you're doing these problems, you kind of know what the units come out to be. It's not a complicated enough problem that you're going to really run into any issues if you don't write your units, but it's still a good idea to keep the units written down at all times just to make sure that you're doing the right thing. And when you're doing more complicated unit conversion problems, then it becomes particularly important. Okay, so I'm going to give you guys a problem here. I would like you guys to pause the video for a few minutes and see if you can work this problem out, and then after you do that, then I'm going to work it out and you can see if you got the same thing. So let's see if you can do the same problem, but with 45 degrees. All right, so I'll give you a moment to pause it, and now we're back. So hopefully you guys were able to figure that out, but let's take a quick look at how that goes. Same exact idea as what I did. I'm going to take 45 degrees, and I'm going to multiply this by my conversion factor of pi over 180 radians per degree. Degrees cancel, and it gives me 45 pi divided by 180, and because the degrees canceled, we are now in radians. Sorry, I'll get out of the way of the light and let you guys hopefully be able to see this. Okay, well now you just have to cancel the 45 and the 180, and that's just a matter of simplifying your fractions. So when you cancel out the common factors, well, it turns out 45 actually divides 180 4 times. So what I actually end up with here is going to be pi over 4 in radians. Hopefully that made sense to you guys. If it didn't, feel free to send me a question and ask me what's going on, and we can talk about it further. Now, what if we wanted to go the other way? So let me ask you this question. Let's suppose that I wanted you to convert let's say that I want to convert 2 pi over 3 radians to degrees. Now, before I show you how to do this, I encourage you guys, again, pause this for a minute, take a minute to try to answer this yourself, and see if you can work this out. It's a little different than what we just did, but it's very much the same kind of idea. Okay. So hopefully you took a minute to think about that, and let's go ahead and see how you can do this. Well, we know what this is in radians. We know it's 2 pi over 3 radians. Okay, so what do I want to multiply this by? I've got to multiply it by a conversion factor, and I want to end up with degrees, so I need to do degrees per radian. Well, we know that there are 180 over pi degrees per radian. Remember, this is one of the conversion factors that we worked out a few minutes ago. So, we have this conversion factor. My radians will cancel. That's good. It leaves me with degrees. Okay, so then what happens? There's actually another cancellation here. The pi's are going to cancel. Since I have a pi in the numerator and a pi in the denominator, those are all going to cancel. I am left with, what am I left with here? I'm going to have 2 times 180 divided by 3 in degrees. Well, 3 cancels with the 180 to leave me with 60. So this becomes 2 times 60 degrees. And what is 2 times 60? Well, that's just going to be equal to 120 in degrees. So we end up with 120 degrees for our answer. Hopefully everybody was able to figure that out on your own. If not, I hope that this explanation made sense to you guys and cleared everything up for you. So converting back and forth here between radians and degrees, you just have to get used to what the conversion factors are. There's a pi floating around, but it's not really fundamentally any different than the kinds of conversion problems you've done before. It's just there's a pi floating around, and you have to remember these two, the pi over 180 and the 180 over pi conversion factors. Now, in addition to converting back and forth between radians and degrees, another thing that we sometimes want to be able to do when we're talking about particularly the geometry of circles is we want to think about the area of wedges. Now, in order to explain what this means, I need to tell you what a wedge is, but if you're feeling like you want to take a little break here and clear your mind before you start this, feel free to pause this, restart the video when you're feeling a bit fresher, because we're moving on to a slightly different kind of question here. All right, so areas of wedges. What do I mean by a wedge? Well, we've actually kind of seen these wedges before when we were talking about these circles. So suppose that I have a circle, and I'm going to say that the circle just has radius r because I want to work out what this is in general. A wedge is this piece of a circle, something of this shape. It's the part of a circle that is inside of some angle. Now, you can have relatively small wedges like this. You could also have very large wedges, like maybe I want my angle to go all the way over to here, and I want to think of this whole Pac-Man shaped piece of the circle as my wedge. That's fine too. For that matter, if I went all the way around the circle, then I'd be talking about a wedge, which is literally the entire circle. Seems like kind of a silly thing to do, but you could, if you wanted to, think of it as the whole circle. Okay, so now that we know what a wedge is, we want to know what is the area of the wedge. So let's call this angle in here theta again. I want to call that theta. And how much area do I have inside of this wedge? Sorry, I'm kind of scribbling over the theta here to shade in the wedge, but hopefully you guys can see what's going on. Well, the answer is that it's the fraction of the circle's area that is inside of this wedge. And the area of a circle again, this is something hopefully you guys remember, pi r squared. So, if I have pi r squared in here, then what is the portion of the circle, the fraction of the circle that is inside of this wedge? Well, if theta is in radians, then the area inside of this wedge, the portion that is inside of it, is going to be a fraction of theta over 2 pi. And so this is going to give us this nice pi r squared. Yeah. And so this is going to give us this nice fraction of theta over 2 pi times pi r squared. Let's write that down. And you notice here that we can actually simplify this a little bit because the pi's are going to cancel. And so the area of a wedge is going to be 1/2 theta times r squared. This is another reason why radians are nice as compared to degrees. I could play the same game with degrees, and I could come up with a formula that involves degrees. But the coefficient that would be out front would no longer just be a 1/2. It would be some kind of messy number involving a pi and a 3-digit fraction type thing going on here. It would just be sort of unpleasant, because in order to get the fraction, I would then have to take the angle and divide it by 360, because in degrees, a full circle is 360 degrees. For our case, we just have to divide it by 2 pi, and the pi's cancel and leave me with this nice 1/2. This is another reason then why mathematicians like to work in radians. It makes working out the areas of wedges a relatively simple procedure, honestly. We just have to use this formula. So let's take a look at an example here of using this formula. And let's see if you guys can work this one out. So again, I encourage you, pause this, try to work this example yourselves, and then we'll work it out together. So let's see if we can find what is the area in, not is, I don't know why I wrote is, what is the area in a wedge with an angle of, let's say that we want to do pi over 3 radians and a radius of 12 meters. Remember that m is just the unit symbol for meters. So give this a try, and then we will work it out together. Well, the way that we're going to work it out is we're just going to use this formula. The angle happens to have been given to us in radians, so we're kind of all set to just plug things into this formula and be done with it, okay? So I'm going to say, well, the area here, it's 1/2 theta r squared. And that's all I need to do. 1/2 theta r squared. I have my theta here, which is pi over 3. So this is my theta. That's going to give me 1/2 times pi over 3. And the radius, of course, is given to me in the problem as well. The radius here is going to be 12. So this is going to be times 12 squared. Okay, so this is going to give me pi over 6 times 144. And let's see, how many times does this go into it? It's going to go into it 24 times. So we end up with 24 pi square meters. Let's just make sure that I did that correctly. 20 times 6 would be 120, and then 4 times 6 would give me another 24, and it totals to 144. So yes, we did this correctly. We can double check ourselves that way, because you know me, I always like to make sure that I didn't do something silly with my arithmetic, because it does happen sometimes. Everybody makes silly arithmetic mistakes occasionally. It's why you want to go back and make sure when you get your final answer that you really have something that makes sense. All right, so this is an example of working out these areas using when the angle is in radians. Now, what if the angle were in degrees? So we might want to find the area, but the angle is actually given to me in degrees. Well, there's a pretty nice way of doing this, and maybe you can think of it on your own, how you would do it. If I know how to do the problem in radians, then all I have to do it if it's given to me where the angle is in degrees, all I'm going to have to do is take that angle in degrees and convert it into radians first. So let's suppose that we want to find the area of a wedge with a radius of, let's say that I want to do 2 inches and an angle of 150 degrees. All right, so think about this for a minute, and now we're back, and we're going to try to work this thing out. Okay, so the area of the wedge with a radius of 2 inches, and the angle is 150 degrees. So the thing that we want to do here is we're going to use the same formula, but I have to remember theta needs to be in radians. I can't just use it in degrees. I can't just plug in 150 here. But what I can do is I can say that in radians, I would have 150 degrees times, what should I put over here? Well, it's going to be pi radians over 180 degrees. Degrees are going to cancel. 150 over 180 is the same thing as 15 over 18, and that should come out to be 5 over 6. So we get 5 pi divided by 6. So that is my angle. My radius is 2. Let's see what happens when we apply this formula. We're going to get an area of 1/2 times the angle in radians, that's 5 pi divided by 6. And let's see, then we have to multiply by the radius squared here, so that's going to be times 2 squared. Now, this 2 in the denominator is going to cancel with one of the 2's that's being squared here. So we end up with 5 pi over 6 times 2. The 6 and the 2 cancel and leave me with a 3 in the denominator, and so we end up with 5 pi over 3. Since the distances here are being measured in inches, our units are going to be in inches squared. And there we have the area of this wedge. So when it's given to you in degrees, you just have to convert it into radians first, and then use the standard formula for radians. You could also just plug in the degree conversion and you'd get a different formula for the area in terms of degrees, okay? You could do that in general. But is it really worth doing that? Because then you have to memorize that other formula, and although that's not a super big deal, I don't like memorizing things, I don't recommend necessarily doing that. Just convert things into radians and then use this formula. All right, now, one more thing that we can do that is very convenient with radians is we can talk about things like angular velocities very easily. So let's talk about, first of all, what is an angular velocity? Well, and again, by the way, take a little break here if you're feeling, like your brain is getting overcrowded. Maybe go take a 5-minute stretch or something and then come back and watch this part of the video if you want. Again, moving on to a slightly new topic, it's a good time for a break. Okay, so what is a velocity normally? Well, normally velocity would be distance divided by time. In other words, it's the change in our location divided by the time that we've spent changing our location, going from one place to another. If I go 15 miles over a period of 5 hours, then 15 divided by 5 means that I was moving at 3 miles per hour. What about angular velocity? Well, this is the change in angle divided by the time. Okay, so it's just like standard velocities, except that now we're talking about angles instead of distances. Really, that doesn't ultimately change much of what we're going to be doing here, but we do need to think about how would you work out problems involving angular velocities. And really, the reason that this becomes an issue is because we often have problems where we're not simply thinking about, oh, we know what the change in angle is. We're talking about problems that are a little bit more complicated, where we have to actually figure out what is that change in angle. Well, to give an example of this, let me suppose a car has wheels of, let's say that the radius is 1/2 meters. In other words, the radius is 50 centimeters. Now, I got to tell you, these are enormous tires. Nobody literally has tires with a radius of 1/2 meter unless you have some super special heavy-duty work truck of some kind. But I want to keep the numbers reasonably simple here. I don't want to talk about like, oh, it's got 16-inch rims or something. So let's pretend we've got some really big tires here. And it travels, let's say, 100 meters in 10 seconds. And we want to know what was the angular velocity Why am I suddenly having trouble spelling angular? Angular velocity of the wheels. Well, in order to figure this out, I need to figure out how much did the wheels turn during this time, and then divide how much did the wheels turn during this time by the time that it took to do that, which is 10 seconds in this case. Now, how would I figure out how many times the wheels turned, or really what angle the wheels turned through as they went? Because we have these wheels rolling along. Well, here's the key. If I take the distance that we go divided by the circumference of the wheels, that is going to tell me how many full turns I made. If I then multiply the number of full turns by 2 pi, that is going to give me the angle that they rotated through in radians. So hopefully you guys can like screenshot this or something and keep hold of it, because I have to erase this board now. Let's hope that I remember what this problem is. So 0.5 meter, and it goes 100 meters. So the full turns are going to be given by the distance over the circumference. Now, the distance was given to us in the problem as 100 meters. That's not a big deal. The circumference is going to be 1/2 times 2 pi, because remember, it's 2 pi times the radius, which comes out to be pi in meters. So the number of full turns that I make is 100 meters divided by pi meters. This gives me 100 over pi. Sorry, that looks more like 106. 100 over pi full turns that I've made here. Now, that's the number of full turns. I don't want the number of full turns. I want the angle that these wheels rotated through. So the angle is going to be the full turns times 2 pi. Okay, so that's 200. So what we found here is that I actually went through 200 radians. Sorry for erasing that. I should have warned you. You can always backtrack a bit here and look at what I just wrote if you didn't get everything down in your notes yet. Okay, so if the angle is 200 in radians, then what is the angular velocity? Well, it's that 200 radians, that's the total angle that we went through, divided by the time. So, angular velocity is going to be 200 radians divided by 10 seconds. That comes out to be 20 radians per second. Okay, so hopefully that made sense to you guys. Another type of problem that we might want to ask is, let's say that we have wheels and we know their angular velocity, and we want to know what does this translate into in terms of the velocity of the vehicle moving forward. This is the kind of problem that actually is very practical, okay? If I'm designing, let's say, a speedometer for a car, I can't measure how fast the car is literally moving, but what I can measure using sensors on the car, I can measure how fast the wheel is turning, and I know the radius of the wheel, at least approximately I know the radius of the wheel. So I can set up a little program that says, okay, this is the angular velocity of my wheel. This translates into such and such an actual linear forward velocity. This is how fast you're actually going when your wheels are spinning that fast. So let's suppose that a car with wheels of radius, let's say that the radius of them is 1 foot, has wheels spinning at 15 radians per second. And we want to know what is the speed of the car. Well, our basic question is, if I go through 15 radians, what is the distance around the circumference that the wheel goes? Because basically, as the wheel is turning, the ground is contacting the wheel at this bottom point. So as it turns, the distance that we go through on the wheel is the distance that we go forward. And then that gives us a distance, and we're going to have a distance per second. So our answer is that we are going to go 15 radians times 1 foot per radian per second, which is going to come out to actually be just 15 feet per second. So that is how fast this car is going. Now, obviously, usually we want to measure cars in things like miles per hour. But once you have it in feet per second, it's a simple enough matter to convert this into miles per hour or whatever other units you might want to measure this in. So this just shows you how do we go from the angular velocity to the linear velocity of the car. The linear velocity meaning how fast this car is actually moving through its, path of travel or whatever you want to call it. You might notice here that something really quite nice happens. You just have the radians times the radius, and that gives you this distance along the circumference. Well, yeah, that's the whole point. That's what makes radians convenient. 1 radian is an arc length around a wedge that is equal to the radius of the circle. And that fact, that geometric significance here, is one of the reasons why radians work out to be so convenient when we're talking about doing things in mathematics, doing things in geometry. Like I said, degrees have their place too. Degrees are good. Engineers like to use them. They're convenient because you don't have to worry about things like multiples of pi and all that sort of stuff that you may not want to worry about if you're just trying to do some kind of engineering problem. But for a lot of situations, radians are actually the more convenient unit. All right, so I'm going to stop there for today's lecture. Remember, you can always go back and forth, rewatch parts of this if they didn't make a lot of sense to you, and make sure to contact me and let me know if you end up having any questions. So good luck with your studies on this, and I will see you again soon.